Hey, I'm Michael Sigmund, and this is Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to observe the difference between a magnet falling through a non-ferrous tube and a magnet in free fall. After experimentation and data collection, the system was modeled using code. Actual results were compared to simulated results. The actual time was 1.65 seconds, and the simulated time was 1.892 seconds. The physics principles that we use for this lab is first Faraday's law, which we use to find the current in each small ring of the tube. The second one is Biot-Savart's law, which we use to find the magnetic field and force on each current carrying ring. The third is Newton's second law, which we use to update position and velocity of the magnet in code. And the final is Newton's third law, which we use to find the force exerted by the tube of rings on the falling magnet. So for this experiment, we need a roll of aluminum foil, a bar magnet, a smartphone, and a tool to measure the tube distance. The method that we use is we suspend the roll of aluminum in the air so that the magnet exiting the tube will be visible. We suspend the magnet above the roll, position the smartphone camera so that the setup is in view, and press record. We then drop the magnet through the tube. The observations for this lab is that originally predicted the magnet would fall through the tube quickly, but it experienced some resistance and fell much slower than expected. The magnet enters the tube straight down vertically and exits the tube down vertically. So through 5 trials, the average time was 1.65 seconds for the magnet to go through the tube. The aluminum roll length was 0.312 meters, the width was 0.0083 meters, the radius was 0.015 meters, and the mu mag that we found from lab 3 was 2.24. The next step of the lab is to create the code. In the first part, I set up the constants, and then in the second one, I set up the tube to be separated into sections of rings. And then the final one, I created the magnet and the tube that it goes through. The second step is to create the magnet at rest, and then after that is to make a function to find the magnetic field and d flux dt. The next section is for the visuals of the output, and then for the calculation of current, magnetic field, and total magnetic force around each ring. And finally, I created code to update the velocity, force, and position of the magnet at each time interval. And when the program is run, you can see the magnet go from the top of the tube to the bottom, the tube is the black cylinder. The red part of the magnet shows the increasing current below the magnet, and the blue part of the magnet shows the decreasing current above the magnet. And you can see on the graph that at about 1.892 seconds that the magnet has reached the bottom of the tube. From this, we can calculate that the free fall would be much faster than dropping the magnet in the tube, and it would be faster at about 12.8% than just a normal free fall. Finally, the concluding questions. The first one is, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So this would increase the induced current, and the magnet would fall slower. And the second one is, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would reduce the number of complete rings making up the tube, the induced current would decrease, and the magnet would fall faster.